Now, with this particular problem here, a rectangular box with a volume of 162 cubic feet is to be constructed with a square base and a top. The cost per square foot for the bottom is 20 cents, for the top is 10 cents, and for the sides is 3.5 cents. What dimensions will minimize the cost? Okay. So it says here minimizing the cost. So we'll be looking at taking the derivative of the cost function. So that's what's changing. And we know that where you have a maximum min is where the slope will be equal to 0. So you'll be minimizing the cost. And we're given that relationship here with the volume on the box. So it's going to be x squared times y is equal to 162 for the relationship here. Okay, so when we have this cost function here, notice the cost function is written in two variables. So we have to rewrite it with just one variable. So I take that volume function and I solve it for y here. Then I substitute it in and replace it. Now the function is written in one variable, x. Okay, and I simplify it a little bit, and I get this function here. From here, I can just take the first derivative because we're interested in minimizing the cost. So we want to know that what that first derivative is going to be for the cost function. So I take the first derivative here. Okay. So since it's minimizing the cost, we're interested in where the slope will be equal to 0. So we set the function equal to 0 and solve for x. Okay. So I'll move 60x to the other side. And then I multiply both sides by x squared. And I divide both sides by a negative, makes that a positive there, and that's x. Now I have x cubed here on this side. Divide both sides by 60. X is equal to 3.4. So I know the x coordinate for the maximum here, the critical point, is going to be at 3.14. So at that location I have a max or min. Since I have one critical point here, I can use that rule that talks about that there's only one extremum. And we can find that if it's a max or min by taking the second derivative here. And whatever that second derivative tells us, whether or not it'll be a max or min at that point. So I come here and I take that second derivative. And I evaluate it at the critical point, 3.4. When I simplify it, I get a positive number here. I get a positive number. So that means that it's going to be a minimum. Because when I have a positive number, it's positive. That means I have a minimum here at 3.14. So the cost to be minimized at the x coordinate of 3.14. What is the y coordinate going to be? The output. So I plug back in here and solve for y. Y is 14. The dimensions so the height is going to be 14. And the width is going to be 3.14. So for the side we have 3.14 and for the height is 14.